Hey everybody, in this video I want to go through some old exam problems on differential equations that I personally have given to my students in the past in the hopes that it's helpful for current and future students in my classes and also anybody else who happens to be watching. Two types of classes where you might encounter these kinds of problems are Calculus 2, including AP Calculus BC for example, especially if you're learning out of this book by Hughes Hallett, or a differential equations class, especially near the beginning of the course, and especially if you're learning it out of this book by Blanchard, Devaney, and Hall. So there are going to be 6 problems total. I'm not sure exactly how long it's going to take me. They are kind of long, involved problems. I think it's going to be over an hour long here, but we will see. And the very first problem is about Newton's law of cooling. It's a detective murder mystery. A detective finds a murder victim at 3 p.m. The temperature of the body at that moment in time is measured to be 89.5 degrees Fahrenheit. 1 hour later, the body is cooled some more and is now 88.4 degrees Fahrenheit. The temperature of the room has been maintained at a constant 68 degrees Fahrenheit. Here's the key sentence: assuming that the rate of change of the temperature of the body is proportional to, a constant multiple of, the difference between the body temperature and the room temperature. The goal here is to find out when the murder occurred. Okay, so this is a basic problem involving this thing called Newton's law of cooling, which is described verbally in what I've just underlined. We want to show work with the following steps. First, write down your independent and dependent variables, including units. Secondly, write down a differential equation for the rate of change, the derivative of your dependent variable with respect to your independent variable. Third, solve the differential equation for what's called a general solution. We are going to need to separate variables, that's the technique to use, to solve for a function that solves it, though there will be an arbitrary constant involved. 4, find a particular solution to the relevant initial value problem. We're going to find that constant that was unknown in part 3, excuse me. Part 5, find the value of the constant of proportionality based on the original line right here. And part 6, use all this to answer the question. In other words, find out when the murder occurred. Note, we're going to assume the typical normal body temperature of 98.6 degrees Fahrenheit, which is not the same for everybody, but close enough to get an answer. We need to make some simplifying assumptions. Okay, so take it step by step. First, write down our independent and dependent variables. Typically written y and t, though you could use other letters. T is time. Use units that are relevant for the situation. We're talking about a murder at 3 p.m. We're talking about the body temperature changing here over 1 hour. We probably should use time in hours. Should we let t equal 0 correspond to 3 p.m.? Or maybe when the murder occurred? I think it's probably easiest to let it correspond to 3 p.m. And then when the murder occurred will be for some negative value of t that we'll have to solve for. So t equals 0 corresponds to 3 p.m. That's an arbitrary choice. I could have done something different, but it's a natural kind of choice. Y is going to be the actual temperature of the body. Temperature of the body in, yes, non-standard units, degrees Fahrenheit. Could do this problem in degrees Celsius as well. All right, that's step 1. Step 2. Let's use a different color here. Write down the differential equation for the rate of change of your dependent variable y with respect to your independent variable t in terms of the derivative dy dt. So what is that? Newton's law of cooling, which should make intuitive sense, again, is that the rate of change is proportional to the difference, a subtraction, between the body temperature y and the room temperature, which is 68, and held constant at 68. So this is going to be proportional to some constant multiple of that difference. You could write the constant multiple as, well, let me leave a little space here initially. Let me go ahead and write a k there as my initial constant of proportionality. But then I'm going to put a negative sign in front of it. Maybe you want to pause the video and think about why I might do that. Times, in parentheses, the temperature of the body minus the room temperature, y minus 68. k here, as I've written it right now, is actually not the constant of proportionality unless I allow it to be negative. It is going to be a negative constant of proportionality here because when the body's cooling and starts out higher than 68, y minus 68 will be positive, but dy dt will be negative. The slope of the solution will have to be negative. The temperature is going down over time. So I could either just say k is a negative number, or maybe I could put a negative sign in front of it and emphasize that k itself will be positive, so negative k will be negative. Okay? That's probably the most natural way to do it. That's your differential equation. We also have an initial condition that y of 0 equals 89.5. We will use that, though let's not bother with that right now because we're not asked to write down the initial condition. Let's move on to step 3. Solve the differential equation. Show your work. All right, so you should have learned the method of separation of variables. The method of separation of variables does not always apply. You can't always use it. The equation itself needs to be separable. What does that mean? It means all the y's need to be on one side and all the t's need to be on the other side. Those are the two variables. The k and the d's in the derivative notation are not truly variables. dy, you might say, is a variable, and dt is a variable. dy is related to y, dt is related to t. What you can do, and this is not rigorous math, though it can be justified, is you can pretend that dy dt is a fraction and try to get the dt on the right side by quote-unquote multiplying both sides by dt and pretending that it cancels on the left side. That's not really what's going on, but for the most part it doesn't hurt to assume, to pretend that that's what's going on. So that will get dt on the right side, but then I'll still have a y minus 68 on the right side. I want to get rid of that y, so divide both sides by y minus 68. After doing so, both multiplying both sides by dt and dividing both sides by y minus 68, the equation looks like this. And at this point, I kind of always joke with my students that you start trembling and saying, hey, that looks something like something I must integrate. And so you go ahead and you give in to that and you go ahead and integrate both sides. Whenever you see a dy on one side and a dt on the other side related by some equation like that, it's a temptation that is usually a good idea to give into to go ahead and integrate both sides. Integrating the right side is pretty easy. That's negative kt plus some arbitrary constant. I could call it c. Let me call it c1 because there's going to be other c's. What about the left side? Hopefully you see pretty quickly that is not too hard to integrate either. It's the natural log of the absolute value of y minus 68 plus some constant, I'll call it c2. Now you can subtract c2 for both sides and say the natural log of the absolute value of y minus 68 is negative kt plus c1 minus c2. Well, you might as well call that c3. Okay? Sometimes people are sloppy here and they don't bother with the subscripts. As long as you get the right answer and don't mess it up, it's okay. We want to solve for y. That's the goal. We want to get rid of the ln then. Exponentiate both sides. This is a little bit sloppy to write it like that, but go ahead and do that. Then the e and the natural log are inverse functions. They cancel. I could write the absolute value of y minus 68 equals, well, I can also use a property of exponents, e to the c3 times e to the negative kt, and e to the c3 I might as well just call another constant c4. Where since e to the c3 would be positive, I guess c4 would have to be positive. And again, I'm not doing rigorous math here, but it does get the right answer. I'm going to go ahead and get rid of the absolute value signs and maybe call this c5 instead of c4, or maybe I think I'll just call it c right now, where c could be positive or negative, and in fact c even could be 0. I'm almost done. I've solved for y now by adding 68 to both sides. I get y is 68 plus c e to the negative kt, where the c is arbitrary. That's an arbitrary constant. This will be a solution of the differential equation no matter what c is. K itself, though, is not arbitrary. That's what you might call fixed. It is the k that is the constant of proportionality in the differential equation. We will actually need to solve for its value based on the initial condition and how much it cooled to 1 hour after the body was found at 3 p.m. Not going to take the time to double check this. You could check it by that it solves the differential equation by first taking its derivative. Just mentally do that. You'll get negative kc e to the negative kt. You get an extra factor of negative k because of the chain rule. And then if you also plug it into the right-hand side by first subtracting 68 from it to cancel the 68, and then multiplying by negative k, actually mentally, you don't even have to write it down. You can mentally check that it is a solution of the differential equation. You get negative k times c times e to the negative kt, no matter which side you plug it into. Those are equal for all t. All right, so we've done step 3. On to step 4. Find a particular solution of the relevant initial value problem. The initial value problem includes the initial condition that at 3 p.m., which is time 0, the temperature of the body was 89.5. If we plug in t equals 0, y equals 89.5 into our solution, we should be able to solve for c. And that would give us the relevant solution of the IVP. We still haven't figured out k yet. That's okay. No pun intended. Go ahead and figure out c first. Again, 89.5 is the initial temperature at 3 p.m., which is time 0. Plug in t equals 0 here. You're going to get e to the 0, which is 1. 1 times c is c. This just simplifies to c. And then I can solve for c by subtracting 68 from both sides. 89.5 minus 68 is going to be 21.5. It looks like the unique solution of the initial value problem is 68 plus 21.5 times e to the negative kt, where again, k is some fixed number that matches the k up there. We still don't know what it is for the situation. Okay, that is your unique solution. That is one function when k is fixed. This represents infinitely many functions because c is arbitrary. Any c will work. That's an infinite family of solutions called a general solution. This is a particular solution to an initial value problem. All right, step 5. Find the value of the constant of proportionality, which is, again, not really k, it's really negative k. So I need the other condition that 1 hour later at 4 p.m., the body has cooled to 88.4. That will help me solve for k. So plug in y equals 88.4. Plug in, think about what would t be? You'd plug in t equals 1, right? 1 hour later. E to the negative k times 1 would be e to the negative k. That's an equation we need to solve for k, and you can see we're going to have to use logarithms. So first subtract 68 from both sides. That will imply that 20.4 equals 21.5 e to the negative kt, k times 1, which is k. Divide both sides by 21.5. E to the negative k is 20.4 divided by 21.5. Take the natural log of both sides. You'll get a negative k on the left, and you get the log of this thing on the right. You'll need to also multiply both sides by negative 1. Looks like k is the negative, the opposite of the natural log of 20.4 divided by 21.5. That will be a positive number, right? Because you take the log of something less than 1, it's negative. The negative sign out there makes the entire expression positive. Let's see what it is. ln 20.4 divided by 21.5 is negative 0.0525. Now I want to put the negative sign in front of that and get positive 0.0525. I think I'll take it a couple more places. 0.052518. That's too many significant figures in reality, but you know, as long as you just round at the end, you're going to avoid round off errors. So I always like to keep a little extra significant figures along the way. So that's what k is, and that satisfies part 5. We have found the value of the constant of proportionality. Actually, negative k would be the constant of proportionality. But it's fine to just write k. Finally, 6 is use all this to answer the question, when did the murder occur? So now we need to solve for the unknown time, t, when the temperature was 98.6, right? It started cooling when they died. So set 98.6 equal to 68 plus 21.5 e to the negative kt, where k is this number and then the t is unknown. So negative 0.052518, the negative sign needs to go in there because then they're in the solution right there. Solve this for t. Subtract 68 from both sides, divide both sides by 21.5. We can write e to the negative 0.052518t would be 98.6 minus 68 is 30.6 divided by 21.5. Take the log of both sides, divide both sides by negative 0.052518. We are going to get a negative answer for t here because the murder happened before 3 p.m. T is going to be, the natural log of 30.6 divided by 21.5, which is positive, divided by the negative number, 0.052518. We are going to get a negative final answer. So natural log of 30.6 divided by 21.5 divided by negative 0.052518. I didn't bother putting the negative sign in there. My final answer is about negative 6.72. About 6 3/4 hours before 3 p.m. That would be 8:15 a.m. So the murder happened at about 8:15 a.m. That would be the answer to the question. About 6 3/4 hours before 3 p.m. All right? And yeah, now I'm rounding essentially. You might even say we should round to 8 a.m. instead of 8:15, but let's go ahead and keep it like that. All right, so that's the first of, again, 6 questions. On to the second question. All right, glance over this, you quickly realize it's a logistic growth problem. P is a population growing according to a logistic model. If you learned about differential equations, you've seen this before, most likely. P is the number of walleye, which is a kind of fish if you've never heard of it before. In Lake Mille Lacs, this is a lake in Minnesota. It's probably got a lot of walleye. I would guess millions of walleye. This is in millions of walleye. It actually did not look that up, so I don't know for sure, but that seems reasonable to me. It's a very big lake. You can't even see across it when you're on the shore. Let t be time since the start of 2016. So we're saying t equals 0 is like stroke of midnight into 2016. Suppose the population P in the absence of fishing follows, like I mentioned, a logistic model with a small population growth rate K that's 0.05 or 5% per year. So when the population is small, that's the essentially continuous growth rate. And as an exponential growth, it would be following e to the kt closely when the population is small. But it also has something called the carrying capacity, L, of 40 million walleye. That is the theoretical limit at which the population would still grow toward. If the population was above that to start with, then more fish would die off than would be born, and the population would decrease toward the carrying capacity. This is the model, dp dt equals 0.05 p times, in parentheses, 1 minus p over 40. This is something where when p is close to 0, this term right here is very close to 1, so you can kind of ignore it, and you get dp dt is 0.05 p, which is an exponential growth. But on the other hand, when p gets close to 40, then this thing gets close to 0. The entire dp dt expression gets real close to 0. Part A, if the initial population is 10 million, so we have an initial value problem here, find p of t, that's our goal, is to find a formula for the solution of this differential equation based on that initial condition, the solution, the unique solution of the initial value problem. Find the population as a function of time since the start of 2016. Part B, make a rough sketch of the slope field for this problem and sketch the solution curve in the slope field. And part C, determine how long it will take for the population to reach 30 million based on it starting at 10 million. And it could be a real long time. And in fact, I think the answer does turn out to be kind of a long time. It's an oversimplification. This doesn't take into account fishing. And plenty of people fish on Lake Mille Lacs, so if you took that into account, it does change things. So this is in the absence of fishing. All right, so we need to start by taking the differential equation and solving for p. Separate variables, just like in the first problem. It's a little harder in this case, though. We do want to get the dt on the right side. So, and there's no ordinary t's on the right side, so you don't have to divide by t, or keep some t expression in t there. We do want to divide by everything on the right that involves p and 1 minus p over 40. If we do so, we'll get the expression dp over p times 1 minus p over 40 equals 0.05 dt. And again, this is like where you start shaking and saying, I must integrate this. Integrate both sides. Once again, the right side is easy to integrate. 0.05 t plus, let's call it c1. The left side is a bit trickier to integrate. And hopefully in glancing over that, you see that we are going to need partial fractions. I also could, if I wanted to, multiply the top and the bottom of the fraction that I'm integrating by 40. If I do, I'll get 40 on top, and I'll get a p times, if I distribute the 40 through, I'll get 40 minus p on the bottom, and I can put the dp over there. This integral is done with partial fractions. You want to break the integrand fraction up into two pieces. Some constant, call it a over p, plus some constant, call it b over 40 minus p. We want to solve for a and b. We want this equation to be true no matter what p is, as long as we're not dividing by 0 here. So multiply both sides by the expression p times 40 minus p to get cancellation. You'll get complete cancellation on the left, you'll get partial cancellation on the right. This p will cancel with this p after multiplication, leaving me with the a and also a 40 minus p. And then with the second fraction here, the 40 minus p's will cancel, leaving me with b times p. Now, technically speaking, you might think, okay, we need to rearrange this and get the expressions involving p together and the constant term by itself. Set it equal to 40. You want it to be true for all p, but you also can get away with, it turns out, just substituting in some values for p, like p equals 0, for example. We'll make this term go away. 40 minus 0 is 40. I'll get 40 equals a times 40. In other words, a must be 1. And if you plug in p equals 40, that term goes away. And this term over here becomes b times 40, 40b. So b must also be 1. Okay, a and b happen to be equal here. That doesn't always happen. You should be aware that that does not always happen. So now we can do this integral as the integral of 1 over p plus 1 over 40 minus p. The 40 in the numerator back here went away because in solving for a and b, we find what makes this equal to that. And you can always double check it by adding these fractions, by getting that common denominator of p times 40 minus p. You'd have a 40 minus p up here if you did that, and also a p up there, and the p's would cancel, leaving you with a 40 in the end, just like you see here. Do this integral. You're going to get natural logs involved. Integral of 1 over p will be natural log of the absolute value of p. Be really careful with the next one. It's not natural log of the absolute value of 40 minus p. It's minus natural log of the absolute value of 40 minus p. You do need that minus sign in there. It is essential. Why? You can think about it two ways. If you are guessing, you can check this by differentiation. And when you differentiate this, including the minus sign, it becomes a plus sign because the chain rule implies that you also multiply by another negative 1, which is the derivative of 40 minus p with respect to p. You can also do it by substitution, say u equals 40 minus p. d would be the negative dp, So a negative sign would come in either way. I could say this is plus C2. I want that to equal this. I can subtract C2 from both sides. I can use a property of logarithms. This is real essential too. One of the most fundamental kind of applications of properties of logarithms, that the difference of two logs is the log of their quotient. And I can also put the absolute value sign outside the quotient like this. And subtracting C2 from both sides, I can also write a plus C3 on the right side, where C3 is really C1 minus C2. Once again, I can exponentiate, just like in the first problem. Get rid of the logarithm. I can also get rid of the absolute value signs. I will get that P over 40 minus P is, let's call it C4 actually. I could call it C here, but I think I'm going to maybe change what the C is one more time. This is positive 0.05 t right there. So I'm going to call it C4. Still a little tricky. I want to solve for P here. It's not quite as simple as the last one. I've got a fraction there where both the top and the bottom have P's. Cross multiply. In other words, multiply both sides by 40 minus P. You'll get P equals 40 C4 e to the 0.05 t minus C4 times P e to the 0.05 t. Multiply negative P times this. Rearrange so the P's are all on the left side, and factor out a P. I'll get 1 plus C4 e to the 0.05 t times P equals 40 C4 e to the 0.05 t. Now just divide both sides by this to isolate P. So it looks like one form of a general solution is 40 C4 e to the 0.05 t divided by 1 plus C4 e to the 0.05 t. A more common thing to do here at this point is to now get rid of the exponential function in the numerator by doing what? By dividing the top and the bottom by e to the 0.05 t. I think I'm also going to divide by C4. Not that I have to, but I think I'm going to do that. So I'm left with a 40 on top. Divide this by C4 e to the 0.05 t. It gives me a 1. I could put the 1 here, but I could also put it over here. Divide 1 by C4 times e to the 0.05 t. I'm going to get 1 over C4, which I'm going to call just C, e to the negative 0.05 t. And that is a negative 0.05 t now. Dividing by e to the 0.05 t is the same as multiplying by e to the negative 0.05 t. So that's sort of the most typical form of the general solution here. But we also want to solve the initial value problem. And so we need the initial condition. By the way, this is not necessarily completely ideal because it doesn't quite give you all solutions. In particular, it is missing a solution at p equals 0, the constant function p equals 0. Let's use the initial condition now. P of 0 is 10 million. The units of p are 10 in millions. 10 equals 40 over 1 plus c times e to the 0, which is 40 over 1 plus c. So that means 1 plus c will equal 4, right? Multiply both sides by 1 plus c, divide both sides by 10. So c is 4 minus 1 is 3. So the unique solution of the initial value problem is p equals 40 over 1 plus 3 e to the negative 0.05 t. That finally is the answer to A. Part B, make a rough sketch of the slope field and sketch the solution. Can this be done without technology? Yes, it can. Maybe you also want to use technology, but it can be. What you need to do is you need to look at the right-hand side of the differential equation and think about when this quantity is positive, negative, and 0. It's 0 when p is 0. It's also 0 when p is 40. So solutions have a 0 derivative for all t, in fact. When p equals 0 or p is 40. Those are called equilibrium solutions. And the slope field will have horizontal slope marks with slope 0. When p is between 0 and 40, this expression is positive. It's a positive times a positive, in fact. 0.05 is positive. dp dt is positive. You're going to have positive slope marks in between 0 and 40. And you're going to have negative slope marks elsewhere. Slope marks with negative slope, I should say. So in a TP plane, well, again, at 0, p equals 0, you can have a bunch of horizontal lines. Also at p equals 40, you'll have a bunch of horizontal lines. Between p equals 0 and 40, in this autonomous differential equation, you're going to have slope marks with positive slopes. And in fact, if you think about it even more carefully, when p is 20 is when this quantity would be maximized and dp dt is maximized. The slope marks have highest slope when p is 20 and slopes that are closer to 0 otherwise. And they're constant slope along horizontal lines because along horizontal lines, that's where p is constant. It's an autonomous equation. You don't see t's on the right side. T doesn't affect the slope field. That means solutions are horizontal translations of each other, at least in these different regions. If p is above 40, you get slope marks with negative slopes, and they get more negative the higher you get. If p is below 0, you get negative slope marks as well, slope marks with negative slope, and they get more and more negative in slope as p becomes more and more negative. So solutions are, for example, 0, 40. Those are two constant function solutions called equilibrium solutions. Solutions up here go down. Solutions down here go down. The most interesting ones, most relevant ones for us are in the middle and with an initial condition of 10. Solution which must follow the slope field looks about like this. Why does it have to follow the slope field? Because that's the geometric meaning of the equation. I want the slopes of my solution curves at any point in the plane to equal 0.05 times the second coordinate of that point times 1 minus the second coordinate over 40. These little line segments have to be tangent to the curve whenever the curve passes through the middle of them. So the solution looks about like this when t is positive. You could also go backwards in time to negative t's as well if you wanted to see what happened in the past. All right, that's the geometry. Part C is an algebra problem to determine about how long it's going to take to reach 30 million. So I need to set this equal to p equal to 30 and c equal to 3, which is what it was before, and solve for t. I'm using this really. Solve for t. And so you need to cross multiply and rearrange and use the logarithm. If we cross multiply, in other words, multiply both sides by this, we're going to get 30. I can also divide both sides by 30. 1 plus 3 e to the negative 0.05 t will be 40 over 30, which is 4/3. Subtract 1, then divide both sides by 3. E to the negative 0.05 t will be 1/3 divided by 3 is 1/9. Take the log. Divide both sides by negative 0.05. Looks like t is natural log of 1/9 divided by negative 0.05, which is a positive number. And using properties of logs, you can also write the top as negative natural log of 9. The simplest form for t here is natural log of 9 divided by 0.05. And then use your calculator to find out about what that is. Natural log of 9 divided by 0.05. ln of 9 divided by 0.05. About 43.9 years. Probably best to round that to 44 years. A long time in the future. Okay. But again, the model may not be accurate. If k were bigger, then the population would grow faster. It's also not taking into account fishing, so it's still not completely accurate. All right, on to problem 3. Some of these problems are not quite this long. So hang on, I think we can do this one pretty quickly here, at least if you know how this kind of problem goes. Also an Euler's method problem that goes pretty quickly. We have a system of differential equations here called a predator-prey system. You think about both of these equations as a unit. You want them to be both true for solution curves at the same time, where a solution curve consists of a first coordinate or component as a function of time, and a second coordinate or component as a function of time. It's really a parametric curve. And the rate of change, the derivative of the first component with respect to t, always equals -2 times the first coordinate, first component value at that value of t, plus 4 times the first times the second. And this is true no matter what t is. And then it's got to be true for the second equation as well. Part A asks to identify which variable represents the predator and which one represents the prey. I think it's unfortunate that both of those words start with the same 3 letters, PRE, at the beginning, because I think it's pretty easy to get them confused. I mean, the word predator does have a pretty common connotation in people's minds to think an animal that eats other animals. But prey, you kind of have to spend a second to think about it, that, oh yeah, prey is the one that gets eaten. So the predator eats the prey. Interactions with the predator are bad for the prey's growth rate. Interactions with the prey are good for the predator's growth rate. See a positive sign right there, a positive coefficient of x times y, and a negative coefficient of x times y there. The positive coefficient, this is called the interaction term when you see the x times y, tells you that when y is, say, large, and also if x is large, definitely dx dt is most likely to be positive. This might overwhelm the value of this. Growth of one of the animals, the x animal, when y is and x are both large, say. This has got to be the predator. The predator benefits from the interaction with the prey. The interaction term for the prey's equation has a negative coefficient again. The interactions between x and y, when x and y are both large, say, make this quantity negative, a large negative number, and this may be a moderately small positive number. dy dt could be negative. Interactions with the predator are harmful to the prey. So x is the predator and y is the prey. X equals the predator and y equals the prey. And again, if you had to give reasons, you'd say exactly what I just said. Interactions with y help x, tend to make dx dt positive, or at least not as negative as it might be otherwise. And interactions with x hurt the prey. By the way, the order of these equations is arbitrary. I could have switched them around. I could have let x be the prey and y be the predator. And then I would have dx dt as this thing, switch around the x's and the y's. And then dy dt would be this thing where you switch around the x's and the y's. So the order that you do these in doesn't matter. But it does matter as far as how to answer this question based on a given order. Part B, the points 0, 0 and 0, 2 are definitely equilibrium points, which are dots shown in this picture at the origin. There's 0, 0, and at this point 0, 2. What do those really represent? We call them equilibrium points, but they're really equilibrium solutions. Their graphs are not horizontal lines because I'm not graphing them literally here as functions of t. I need to imagine time going by. But they are constant functions as parametric curves. The no curve gets traced out as t varies. It just stays at one point. That's what an equilibrium point is, and I could call them equilibrium solutions as well. But we want to show algebra work to verify that this point, 3/4, 1/2, which is right here, is also an equilibrium point. Okay? Now, there is a quick way to do this that really doesn't involve doing much algebra. though you do need to do arithmetic. And that's to just assume this is right and plug those x and y values into the right-hand sides of the differential equations and see that you get 0, because that's what has to happen in equilibrium points, is both of these differential equations have to be identically 0 at equilibrium points. So you can do that. You can also try to algebraically solve for it. Technically speaking, logically speaking, it's the verifying that it's the plugging in that really truly proves that these are equilibrium points. So it's not only quicker and easier, it's technically more correct. When you plug, again, x is 3/4, y equals 1/2 into this expression, -2 times 3/4 plus 4 times 3/4 times 1/2, do we get 0? This simplifies to -3/2, and this simplifies to +3/2. We do get 0. I also need to check the second equation. 2 times y is 2 times 1/2 times 1 minus 1/2 over 2 minus 2 times x, which is 2 times 3/4 times y. This should simplify to 0 as well, hopefully. 2's cancel there. This is 1 minus 1/4, which is 3/4. The 2's cancel here. I'm left with minus 3/4. This is 0 as well. Okay. For sake of time, I'm not going to show the other way to do it. Well, I probably should. It's more than just time. We should focus on understanding too. How would you algebraically solve for that third equilibrium point if you didn't know what it was? You want to set both of these equal to 0 and solve for x and y simultaneously as an equation of algebra equations, a system of algebra equations. It's best to do it with the factored forms. And in fact, if we think about letting both of those things equal 0 simultaneously, we quickly see that 0, 0 is one solution. X equals 0, y equals solution makes both of these equal to 0. That's the origin. How about 0, 2? When x is 0, certainly we get 0 on this thing. 2 times 0 times whatever is 0. When x is 0 and y is 2, do we get 0 here? We don't get 0 for this part. 2 times 2 is 4. Do we get 0 here? 1 minus 0 minus 1/2 times 2 is 1 minus 1 is 0. We do get 0 at the other equilibrium point. But if you needed to solve for that, you'd want to ignore these first two parts and set both of these things equal to 0. -1 plus 2y equals 0. And 1 minus x minus 1/2 y equals 0, and solve that system of linear equations for x and y simultaneously. It's a fairly easy one to do because we can quickly solve for y to be 1/2 based on the first equation. Substitute that into the second equation. Add x to both sides. X is 1 minus 1/4, which is 3/4. So you should be able to do it this way in case I didn't give you the answer ahead of time. And especially for the higher level course, differential equations, I might not. So you should be able to solve for it as well. Part C says to use the equilibrium points and the null lines that are pictured and the direction field to sketch an approximate solution curve for this initial condition. Okay, that's a lot of words that maybe you've never heard of before. Equilibrium points are, again, these 3 points, which are really equilibrium solutions. They're constant functions. They're not just points, they're constant functions. But when you trace them out in an xy plane, ignoring t, this always is the same point. These lines that you see are called null lines. This one right here is one piece of what's called the y null line, because look, solutions which follow those arrows, this is called the direction field for the system, must cross horizontally. dy dt equals 0 along that line. As a solution curve crosses that line, it has to cross with a horizontal tangent, because you see these arrows are very close to horizontal there. Likewise, along the x-axis itself, solutions have horizontal tangents. In fact, solutions that start on the x-axis always stay on the x-axis. Y would always be 0 in that case. You also have x-nilk lines. This line here, solutions are crossing it vertically, either going upwards or downwards. And also along the y-axis, solutions have vertical tangents as well. X is 0, dx dt will always be 0. And you can see that from thinking about these expressions as well. If you did not have the drawing, you could use these expressions and graph x equals 0, for example, and y equals 1/2 to get the x-nilk line, and then y equals 0 and this equaling 0 to get the x-nilk line. That equaling 0 would be the x-nilk line. This equaling 0 would be the y-nilk line. And for example, when that part is 0 right there, that's where you get this slanted line. My initial condition is 1.5, which is right about here. And the solution curve, the trajectory, has to follow this direction field. It's analogous to a slope field, except it's graphs of parametric curves, not graphs of ordinary functions. Those vectors that you see, those arrows in the direction field, have to be tangent to the solution curve as it goes through the base of any one of them. And so it seems that a solution curve starting right about here, it's got to look about like what I'm drawing. It's impossible to draw these things perfectly, but you do your best. Sometimes predator-prey systems end up having periodic solutions that come back to where they start, but you can see here we seem to be kind of forced to be really spiraling in toward this equilibrium point. And that makes that equilibrium point have a special name. It's called a sink. Draw arrows along here to indicate the direction of motion for the parametric curve as time increases. So that helps us also do part D, describe the long-term behavior of the populations as time goes by. Both the x and y coordinates are oscillating, but those oscillations are getting smaller and smaller. They're approaching this point. X is approaching, in fact, 3/4. Y is approaching 1/2. If you graphed x and y individually as functions of time, let's see, x would start out at 1, increase initially because I move it to the right, reach some maximum close to 2 before decreasing, then increasing again, but with a smaller oscillation, then decreasing again, etc., and approaching 0.75. 0.75 would be a horizontal asymptote for the function that the function also happens to go through, which is allowed as t increases. And for y, it approaches 1/2 and starts out at 1.5. It's initially going down in value because this point is moving downwards. Reaches some minimum around 0.1 or 0.2 before coming back up again. Reaches that minimum of 0.1 or 0.2 when x is about 1, so that would be more like here actually. Now you're heading back upwards here. Y is increasing, this graph goes up, before decreasing again, etc. Something about like this would be the solution curves as functions of time. And describing their behavior would be just to say the solutions oscillate toward a population of 0.75 for x and 0.5 for y. Okay, and you can draw those kind of graphs. All right. This one's actually a quicker problem. It doesn't look quicker than looking at it here, if you know your stuff at least. It involves some physics. Suppose we got a block of a certain mass, m equals 5 kilograms, attached to a spring. It's a mass on a spring. Suppose the spring has a spring constant, sometimes called a stiffness constant, K equals 49. In standard units, that would be newtons per meter. Don't worry about what newtons per meter means. You can give it meaning, but don't worry about it. Let x be the position, the displacement, in other words, of the mass from its equilibrium. So when it's at equilibrium, x would be 0. When it's, say, to the right of its equilibrium, x would be positive. And when it's to the left of its equilibrium, x would be negative. It's a position or displacement. In meters, keep the units consistent, with positive x-axis pointing to the right. In the absence of any friction or air resistance, so we're assuming like the block is on ice in a vacuum, and assuming the internal friction inside the spring is negligible, that's the most dubious assumption. Absence of friction or air resistance. Use Newton's second law and Hooke's law, 2 laws from physics, to write down a second order IVP, initial value problem, which is a differential equation with 2 initial conditions. Second order means it involves second derivatives. Modeling the position x as a function of time. When the mass is stretched to a position of 0.03 meters to the right, so x0 is going to be positive 0.3. I'm grabbing this mass and stretching the spring that way. I also could compress the mass toward the wall, and the initial x could be 0.3 to the left, which would actually make x negative 0.3. Let it go from rest at t equals 0. From rest means just let it go and let it oscillate. So the initial velocity is 0. That's what that means. Okay, so it's just setting up an initial value problem. You'll need 2 initial conditions, one for the position, one for the velocity. I have not asked this in my Calc 2 classes when I asked this problem, but I have in my differential equations classes. As a bonus, solve the IVP by educated guessing. So if you're one of my Calc 2 students, you won't necessarily need to know how to do that, though you should understand what I'm going to show you when I do the bonus. And if I asked you to verify the solution, you should be able to do that, my Calc 2 students. Just the educated guessing is a little bit beyond our course, though I will give some intuition behind the guess. All right, so a lot of people look at this and they're just like, what in the world am I supposed to do? You need to write down equations that must be satisfied. That's what you need to do. What does Newton's second law say? Newton's second law is typically written F equals ma, right? There's the standard way to write it. Force equals mass times acceleration. The form of the force is different in different situations. We enter a very specific kind of situation. Got a wall here. You got ice down here, say. You have a spring and a mass M attached to the spring. We're in a vacuum, that kind of thing, to keep our air resistance negligible. The force is due to what's called a restoring force of the spring. And if we draw the mass on the spring horizontal, we don't have to worry about gravity because it's canceled out by the upward force of the ice on the mass. If the mass were hanging from a ceiling, technically you do have to worry about gravity, but it turns out that the gravity, it can be justified to ignore it as well there, because what essentially happens is the equilibrium position of the mass shifts when you include gravity. Newton's second law is really a differential equation in disguise. The A is the acceleration. That's the second derivative of the position with respect to time. We get a second derivative in this equation. I could go ahead and write it right away. I could write m times the second derivative of x with respect to t. Using an x because that's the dependent variable here. And by the way, if the mass is at equilibrium here in this particular picture, this would be 0 right there, not over here, not at the wall. So there's the start of the differential equation. It's not the end, though. I haven't used Hooke's law yet. I need to describe the nature of the force. Hooke's law describes the nature of the force. Hooke's law is an example of what we call an empirical law. It's essentially a law based on data, not necessarily, at least at the start, based on theory. And it's actually not a perfect law. It doesn't describe things perfectly, but it's a reasonable approximation. It says that the force, the restoring force of the spring is negative K times X, where K is the spring constant. So it's a negative proportionality with respect to X. K itself is positive, so negative K is negative. Does this make sense for the restoring force? Think about it. Grab the mass, pull it away from equilibrium. The force is going to be in the negative direction. X is positive, but the force is negative. You do need a negative constant. On the other hand, when you squish the mass toward the wall, X is negative, but the force is in the opposite direction. It's positive. Right where it is positive. Once again, it has the opposite sign as X. So there's your differential equation, but we need to plug in M and K. Okay, well, I give you M and K. Go ahead and just plug them in. So K is 49, so I get negative 49X equals M times the second derivative, 5 times, I'll just write it as X double prime now. It's understood that it's with respect to T. I could put an of T in here as well, but it's traditional not to do that in differential equations, and there are good reasons for that. That's one way to write it. You could also divide everything by 5, for example, and rearrange. You could also write this as X double prime plus 9.8X equals 0. Those are equivalent equations. Or X double prime equals negative 9.8X. Any of these equations, and you can also use the Leibniz notation there in place of X double prime. Any of these is okay for the answer, for the differential equation. Not for the initial value problem. We also need these initial conditions. Position 0.3 when t is 0, from rest when t is 0. X of 0 is 0.3. X prime of 0, the velocity, is 0. So when I include those initial conditions as an initial value problem with 2 initial conditions, that is the answer, okay, without doing the bonus yet. Now let's go ahead and do the bonus. Solve the initial value problem by educated guessing. This is something you might have seen in a physics class before. I hope you've seen it. In the absence of friction, mass on a spring like this tends to oscillate sinusoidally. The graph of x as a function of time tends to be a periodic sinusoid, which is not necessarily a pure sine function. It could involve a cosine, or it could even just be a cosine function, and you'd still call it a sinusoid. So we could guess a sinusoid here for the initial value problem. Guess, say, a times cosine of something times t plus b times sine of something times t. Since the initial position is at really what has to be its maximum because you're letting it go from rest, and the initial velocity is 0, it actually makes more sense as an educated guess to just use a cosine, because the graph of cosine starts at its peak and has a slope at t equals 0, which is 0. So I'm going to do that. I'm going to just go ahead and guess x equals, well, I'm going to go ahead and use the 0.3 right away. 0.3 cosine of something times t. It's not clear what the something should be. I'll call it b, but I'm going to need to solve for b. And so for my Calc 2 students, this guessing is something you may not be able to do. But if I told you this was what to guess, then you should be able to solve for b. How? By essentially plugging into the differential equation and setting both sides equal to each other. And you want them to be equal for all t, and that allows you to find b. Let's check it. Here's the first derivative, negative 0.3b sine bt, because I need the chain rule there. B is a constant. The second derivative, I get another factor of negative b, or of b itself, excuse me. The negative sign will stay. I'll get negative 0.3 b squared cosine bt. Plug that into the differential equation here on both sides. So this was x double prime, by the way. I'm going to get x double prime is negative 0.3 b squared cos bt. The right side is negative 9.8 times x, which is times 0.3 cos bt. The negative signs will cancel. The 0.3s will cancel. The b squared is not going to cancel. Do the cosine of bt's cancel? Well, yes, as long as you're not dividing by 0 when you cancel. It's better to just realize that, hey, b squared cos bt will equal negative 9.8, excuse me, 9.8 cos bt for all t if b squared equals 9.8. These will be equal for all t if b squared equals 9.8. Now you could, yes, say, oh, I'm going to divide both sides by cosine of bt. Be careful in doing that. You'd be dividing by 0 sometimes. It's better to think of it this way. I want these to be true for all, equal for all t. The only way that will happen is if b squared is 9.8. So b evidently is plus or minus square root of 9.8. It's good enough to take the plus 1 when you plug it into the cosine function because cosine is an even function. So if I use the minus square root of 9.8, I get the same function really. So the answer for this bonus is 0.3 cosine of square root of 9.8t, and you could approximate square root of 9.8 if you like. You should be able to check that it solves the differential equation. Its second derivative is negative 9.8 times itself. It also satisfies these initial conditions. When you plug in t equals 0, you get cosine of 0 is 1 times 0.3 is 0.3, and then the derivative is going to be this with b replaced by square root of 9.8. When t is 0, that will automatically be 0 because sine of 0 is 0. That's the bonus. That's the unique solution of the IVP. Just 2 more questions. Apply Euler's method, not Euler, but Euler. Euler's method, delta x is 0.5 to approximate y when x is 1.5 for the solution of the differential equation which passes through this point, which in other words satisfies the initial condition that y of 0 is 1. X is 0 and y is 1 there. There's no t's in this problem. Though there could have been, I could have used t instead of x. All right, it's best to do this with a table. You have your step number, so to speak, k. You have your x coordinates, x sub k, which in some problems might be t coordinates. Your y coordinates, y sub k. And then your change in y coordinates, delta y sub k, which Euler's method says to compute by plugging the given coordinates xk and yk into a function f, where f represents the right-hand side of the differential equation as a function of 2 variables. It's a multivariable calculus function times dt, or dx in this case. Okay, and again, it is common to use t's instead of x's here, so you should be able to handle that as well. Now I'm going to go ahead and just do the calculations here. But you should realize in doing them, I'm not really explaining why this works. K starts at 0. We have a 0th step, so to speak, for the initial condition. To get to 1.5 when delta x is 0.5, I'm going to need to do 3 steps. 1, 2, 3 will be the last value of k. The initial value of x is 0. The initial value of y is 1. What is this value? I need to plug these numbers, these coordinates, into this right-hand side function. I need to find, in this case, f of 0, 1, and multiply times delta x, which is 0.5, to find the change in y that I'm going to add to the preceding value of y. Euler's method can be written as what's called a recursive equation. Y sub k plus 1 equals the previous value yk plus the change in y, call it y sub k. That'll be y sub k plus f of xk comma yk times delta x. I'm now in the midst of computing this part right there. Again, I'm not explaining why it works. If you plug in x equals 0 and y equals 1 right there, you'll get 0 plus 2. 2 times 0.5 is 1. The change in y is 1. X keeps going up by 0.5, but y does not change by a constant amount. Its initial change is 1. Y sub 1 is y sub 0 plus 1 is 1 plus 1 is 2. But that will change as I keep going. Because now I need to plug in the point with coordinates 0.5 and 2 into the function before multiplying by 0.5. Plug in x is 0.5, y is 2. 2 times 2 is 4, plus 0.5 is 4.5. Don't forget to multiply by 0.5. This is 2.25. So the next value of y is 2 plus 2.25, which is 4.25. One more step and we'll be there. Our answer will be whatever goes there. That's the y coordinate, approximate y coordinate of solution of the differential equation when x is 1.5. But I need to plug in point with coordinates 1 and 4.5 into the right-hand side function. 1 and 4.25, excuse me. And multiply by 0.5. All right, 4.25 times 2 is 8.5, plus 1 is 9.5. Just double check that. Yeah. Times 0.5 is going to be 4.75. So I'm going to get 4.25 plus 4.75 gives 9 for the final approximation of y when x is 1.5. Should be able to plot these points too. The scale for y is going to have to be bigger. Let's say 10 is here. 5, 2, 1. When x is 0, y is 1. That's the first point. Second point is 0.52. Third point is 1, 4.25. Last point is 1.59. Then you can connect the dots. You could, it's fine just to connect them with, say, straight line segments. We just want a feel for what the solution looks like. You could connect them with curves as well, though that gets more complicated. This is not the exact solution curve, it's an approximation. And the idea behind this is that we are trying to follow the slope field. This would have a slope field. And we're trying to follow those tangent lines. That's essentially what we're doing in doing this product here. Because this is the slope of the tangent line, which is the rate of change, times the change of x itself, giving you the change in y. But it's approximate because solution curves are smooth and they follow the slope field at every point, not just at a discrete finite set of points. That's what my Calc 2 students should be able to do, but let's do the bonus. Solve the IVP by educated guessing, though I will warn you the educated guessing here is harder than the other one. Let's take this differential equation and rewrite it in a different way. Let's rewrite it as this form. Subtract 2y from both sides. It's an equivalent form for this differential equation. In this form, the reason I did this is because it makes it easier to guess. What function, y is a function of x, would have a derivative minus 2 times the function always equal to x? Y is a function of x. What function of x has the property that its derivative minus 2 times the function as a function of x always equals x? Well, you think about that a little bit, and you might guess y is, say, some linear function, ax plus b, is likely to be a kind of function whose derivative minus 2 times itself equals x for all x. Let's see, do any values of a and b work? Take the derivative of this. There's your left-hand side, LHS. Plug these into the left-hand side. In other words, find y prime minus 2 times y. We've already found y prime to be a. Y itself is ax plus b. As a function of x, this simplifies to negative 2a times x plus the constant that can be written as a minus 2b. I want to choose a and b so that this is always equal to the right-hand side, x. Set this equal to x for all a and b, or for all x. The only way that's going to be true is if negative 2a equals 1, and if a minus 2b equals 0. That's the only way these things can be equal for all x. System of equations that can be pretty quickly solved. A is going to be negative 1/2. 2b will be a. B is going to be 1/2 a. 1/2 times negative 1/2 is negative 3/4. Negative 1/4, excuse me. Negative 1/4. So it looks like we have a solution by this guessing. Y equals negative 1/2 x minus 1/4. That does solve the differential equation. However, it does not pass through this point. When x is 0, y is negative 1/4, not 1. So should I just add on a constant here to make it pass through that point? No, do not do that, even though that might seem logical. And it would be okay to do that if this were a pure antiderivative problem, if the right-hand side only involved x. But here, because it involves y as well, distinct solutions are not going to be vertical translations of each other. They're also not going to be horizontal translations of each other. It's non-autonomous. So what do we do instead? If y were ax plus b plus, what function has the property that its derivative is 2 times itself? In other words, its derivative minus 2 times itself is always 0. That would be a good thing to add, because it wouldn't affect the right-hand side. What function has that property? Some constant times e to the 2x would. Any constant times e to the 2x has the property that its derivative gets an extra factor of 2, and it's being multiplied times the original function. It's 2 times itself. If y is c times e to the 2x, that's going to have the property that y prime minus 2y equals 0 for all x. Y prime equals 2y for all x. Doesn't matter what c is. So now, yeah, if I add this kind of function to this, it should still solve the differential equation with an x on the right side. Because this part differentiate when you plug it into the differential equation gives you the x part. When you plug this part in the differential equation on the left side here, you get 0. It doesn't affect the right side. after simplification. It doesn't affect how it matches the right side. So that's what we want to do. That's the educated guessing here, though again, it's trickier. The general solution, in fact, is -1/2 x minus 1/4 plus c e to the 2x. And now I want to choose c to satisfy the initial condition when x is 0, y is 1. This simplifies to c minus 1/4. Add 1/4 to both sides. C is 1 plus 1/4, which is 5/4. And now the particular unique solution of the IVP is y equals -1/2 x minus 1/4 plus 5/4 e to the -2x. Almost made a bad mistake there. Don't forget to multiply by e to the 2x. Okay? And you can double check that. And you could also graph it and compare it to this graph. In reality, the true solution is going to be, because it's concave up, the Euler's method approximation is going to be underneath it. It's going to be too small. That's what you'll see if you graph this along with the original approximation from Euler's method. All right, one more problem. Once again, it's got a bonus part to it. Calc 2 students, you don't need to be able to do the bonus, though I think it's still worth learning about. Differential equation students, you should learn how to do the bonus. It's a method that if you're in calculus, you wouldn't have heard of before. It's called the method of integrating factors to solve the IVP here. This is called a mixing problem. We have a tank. It's a 40-liter tank. It's got 10 liters of pure water to begin with. No salt. But at time 0, salt water, with a concentration of 6 grams per liter, is flowing into the tank at a flow rate of 4 liters per minute. So it's well-mixed salt water. The salt effectively is not taking up any volume, though there's plenty of it. All right, at the same time, t equals 0, a drain is open at the bottom so that the fluid flows out at a rate of 3 liters per minute. That's a little smaller. So it's coming in at 4 liters per minute, going out at 3 liters per minute. The tank is going to gradually fill up. Let Q be the quantity of salt in the tank, not the amount of water, but the quantity of salt. It would make most sense to be in grams because the concentration is grams per liter. And let T be time in minutes since t equals 0. For Calc 2, I told my students to set up, but do not solve an IVP modeling the situation and say for how many minutes it's valid. The bonus says solve. I will do both. But my Calc 2 students, you wouldn't have to do the bonus. But once again, if I gave you the answer, you should be able to verify that's the solution. All right, so how do you set it up? You can make a drawing of the vat if you like. It's not absolutely necessary, but many times people find it helpful, something like this. Emphasize you got to flow in at 4 liters per minute. It's salt water with a constant concentration of 6 grams per liter. Here you've got it going out at 3 liters per minute. And it's well mixed. You assume the salt mixes instantaneously for the water inside, uniformly over the entire vat. That's obviously not true, but it's a simplifying assumption to actually solve the problem, so you can ignore the spatial effects. In reality, if you were trying to fully model this, you'd have to take those into account and think about diffusion of salt. If there's like a fan inside the tank mixing things up really, really rapidly, this is still going to be a good approximation. What's the concentration? I'll put question mark concentration, grams per liter. And that question mark is not constant. It's going to vary. Right away at the start, there's no salt in there, it's going to be zero grams per liter. But then salt comes in, mixes instantaneously. 1 millisecond later, you start to have some salt coming out as well. And since the concentration is going to increase over time intuitively in the tank, this is going to increase over time as well. The essential principle to derive the differential equation is that the rate of change of the quantity of salt with respect to time comes from two sources, a rate in and a rate out. From the salt water coming in, that's rate in, minus the rate out. And the units have to be grams per minute. It's important to think about the units here because it's grams for Q and minutes for T. Both of these numbers do not have units of grams per minute, but if I multiply them, the liters cancel and the final answer is in grams per minute. Yeah, that's how fast salt is coming in. 6 grams per liter times 4 liters per minute. The liters cancel. This is the same as 24 grams per minute. It's a constant rate in because it's a constant flow rate and a constant concentration. To come out, again, we have question mark grams per liter for the concentration. Let me leave a space there. Times 3 liters per minute. Once again, the liters will cancel. But what goes in front of the grams per liter? It's an amount of salt in grams divided by the volume. Q divided by V, say, for volume. Okay, but the volume's changing, it's going up. In fact, it's going up in a pretty simple way. I can figure out a formula for the volume as a function of T. It starts out at 10 when T is 0 and goes up by 4 minus 3 liters every minute. So the volume itself as a function of time is 10 plus T, and you do want to put that in there in place of V. V is not a constant here. It's a function of T. Q is not a constant either. I could write Q of T here and I could put an of T here. It's traditional not to, and there's a good reason for that again. Just leave it as a Q there. So this is going to be, well, if I include the minus sign, minus 3Q over 10 plus T grams per minute. So the initial value problem, which for Calc 2 would be the final answer to this problem, consists of the differential equation dq dt equals 24 minus 3Q over 10 plus T. There's no salt at time 0, so Q of 0 is 0. It didn't have to be that way. I could have had some salt in there to begin with. I could have given it in grams. I also could have given just the concentration, and you'd have to figure out the grams by knowing the initial amount of volume as well to start with. But to keep it simple, so that it's pure water to begin with, no salt. All right, that solves the problem except for the bonus. Now let's do the bonus. If you're a Calc 2 student, this is still worth learning about. It's a pretty interesting little trick related to the product rule that comes into play. Let me, like I did in the last problem, rearrange this equation. dq dt by adding 3Q over 10 plus T to both sides. And when I add it on the left side, I'm going to separate the Q off. I'm going to write it as 3 over 10 plus T times Q. That has to equal 24. To be a solution of this differential equation, Q as a function of time means that if I take the derivative of the function, add this fraction times the function, I have to get, for all values of T, that it equals 24. It has to simplify for all allowed values of T at least to just 24. I guess I did forget to say how many minutes this is valid for. So it was not a complete solution to the original problem. The volume is 10 plus T. Here's where I use the fact that the tank is 40 liters. You're going to get up to 40 liters after T equals 30 minutes. So this is valid for T between 0 and 30. I forgot that. That's the domain for your solution. So it's not clear how to solve this by any means. The method of integrating factors is a method that can help you solve it, but it's kind of weird. You define a new function, typically written as mu. I love the Greek letter mu. Looks like that. Kind of looks like an M. Kind of looks like a U. Some hybrid of M and U, and it's called mu. It literally is called mu. Mu. Mu is called the integrating factor. And mysteriously, its formula is e to the integral of this function dt. What in the world is this? E to the integral of 3 over 10 plus t dt. Let's go ahead and do the integral. You're going to get 3 natural log of the absolute value of 10 plus t, though one simplification we can do is we don't need the absolute value signs. I could put a plus c in here as well, but another simplification is you can take c to be 0. Something else that's nice in this case is you can use a property of logarithms to bring the 3 up here as an exponent, and then use the fact that e to the x and natural log of x are inverse functions to simplify this to 10 plus t quantity cubed. Okay, pretty weird thing to do. What in the world do we use this for? Well, we now take it and we multiply both sides of the differential equation by it and simplify. That makes it a factor. Its name is an integrating factor. Should probably put the full word here, integrating factor. It makes it a factor on both sides of the differential equation. What makes it an integrating factor? Turns out that by defining it in this special way, it makes the left-hand side of the differential equation really easy to integrate, if you look at it in the right way at least. So let's go ahead and multiply it. I'm going to get 10 plus t quantity cubed times dq dt. Plus, when I multiply times this thing, one factor of 10 plus t cancels. I'm going to get 3 times 10 plus t squared times q. Don't forget to multiply it on the right side as well. That's the most common mistake. People forget to do that. But that is essential to get the right answer. These equations essentially are equivalent to each other. If you're a solution to this one, you'll be a solution to that one, and vice versa. Except possibly having to deal with issues of dividing by 0 in the first one. Okay, now I claimed the left-hand side is easy to integrate. It doesn't look easy to integrate, does it? That's where the product rule comes into play. This thing right here, if you stare at it long enough, all of a sudden you realize one day, hey, this is the same as the derivative with respect to t of 10 plus t cubed, the integrating factor, times q. Q really is q of t, but again, it's traditional not to put the of t in there. And again, there's a good reason for that. Keep saying there's a good reason for it. The main good reason is that it helps you think about the slope field in the right way. That's the product rule. Why? We'll just double check it here. You've got the derivative of a product of two functions of t. That's a function of t as well. There's the first function times the derivative of the second plus the second function q times the derivative of the first. The derivative of 10 plus t cubed is 3 10 plus t squared times 1. Yeah. And now integrate that. But if you integrate a derivative, you get the original function. Integrate. That's why it's called an integrating factor. Integrate both sides. The left side integrates to 10 plus t cubed times q. The right side, you've got to actually do the integral. If you integrate this, do not expand this out, just do a substitution, u equals 10 plus t. Or just guess, you'll get 6 times 10 plus t to the 4th power plus a constant. Double check that by differentiation. Now solve for q. Divide both sides by 10 plus t cubed. Q will be 6 times 10 plus t to the 1st power, 4 minus 3, plus c over 10 plus t quantity cubed. This is also 60 plus 6t. Now use the initial condition, q of 0 is 0, to solve for c. 60 plus 0 plus c over 10 cubed equals 0. 10 cubed is 1,000. Subtract 60 from both sides. It looks like c is negative 60 times 1,000, negative 60,000. And therefore, your final answer for the solution of the initial value problem, you can write as q equals 60 plus 6t minus 60,000 over 10 plus t quantity cubed. There you have it. And then you could use this to do various things, and you should be able to verify it satisfies the differential equation in the initial condition. Should be able to graph it in slope field even, and if you did, the graph, I think it ends up looking something like this. You can check that. Q of 0 is 0. And you could, figure out a time when the amount of salt equals, I don't know, 2 grams or something. So you'd set Q equal to 2 and solve for T. Would be an application of this. Okay, so that does it for this video. I know that was a long video. I hope you got a lot out of it. If you watched to the end, that's very impressive. Thanks for watching.